Hi, this is Physics 221, Mathematical Physics 1, and in this lesson we're going to discuss about your Fourier series. You may have already discussed in your previous math classes about how functions, complicated functions, can be expressed as a power series. Another way of expressing these complicated functions is in terms of as a sum of sine and cosine terms. And unlike Taylor series, a Fourier series can describe functions that are not everywhere continuous and or differentiable. Fourier series are often used to represent the response of a system to a periodic input, and this response often depends directly on the frequency content of the input. Fourier series are used in a wide variety of such physical situations, including the vibrations of a finite string, the scattering of light by a diffraction grating, and the transmission of an input signal by an electronic circuit. These are some examples of functions wherein a Fourier series is applied. So you have a square wave, a sawtooth, a triangle wave, and a semicircle. So these waves here, or these other colored graphs, are actually your Fourier series. The particular conditions that a function f of x must fulfill in order that it may be expanded as a Fourier series are known as the Dirichlet conditions and may be summarized by the following 4 points. First, the function must be periodic. Second, must be single-valued and continuous, except possibly at a finite number of finite discontinuities. Third, it must have only a finite number of maxima and minima within one period. And fourth, the integral over one period of f of x must converge. If the conditions above are satisfied, then the Fourier series converges to f of x at all points where f of x is continuous. The convergence of the Fourier series at points of discontinuity will be discussed in the next sections. The last three Dirichlet conditions are almost always met in real applications, but not all functions are periodic and hence do not fulfill the first condition. It may be possible, however, to represent a non-periodic function as a Fourier series by manipulation of the function into a periodic form. This will also be discussed in the following sections. This is an example of a function that may be represented as a Fourier series without modification. So later, we are going to represent some functions as a Fourier series, like for example this one here. We require that any reasonable function, one that satisfies the Dirichlet conditions, can be expressed as a linear sum of sine and cosine terms. Note, however, that we cannot use just a sum of sine terms, since sine, being an odd function, that is a function for which f of negative x is equal to negative f of x, cannot represent even functions. Functions for which your f of negative x is equal to f of x. Again, we cannot just use a sum of sine terms since being an odd function, it cannot represent even functions. So your sine terms or your sine function being an odd function cannot represent even functions. Similarly, odd functions cannot be represented by a cosine series since cosine is an even function. Nevertheless, it is possible to represent all odd functions by a sine series and all even functions by a cosine series. Just a quick review, you may be asked to determine algebraically whether a function is even or odd. To do this, you take the function and plug negative x in for x and then simplify. If you end up to the same, or if you end up with the exact same function that you started with, that is after you plug in negative x to the function, you still get your original f of x, so all the signs are the same, then the function is even. If you end up with the exact opposite of what you started with, for example, if after you plug in negative x to the function, you get the negative of f of x, so all the signs are switched, then the function is an odd function. Now, since all functions may be written as a sum of an odd and an even part, let's say for example here, for your function f of x, which can be written as 1/2 of your even function and 1/2 of your odd function, we can write any function as a sum of sine series and cosine series. All the terms of a Fourier series are mutually orthogonal. That is, the integrals over one period of the product of any two terms have the following properties. First, the integral from x0 to x0 plus L, where here your L is your period, of sine 2 pi Rx over L, cosine 2 pi Px over L, dx is equal to 0 for all R and P. The second one is the integral from x0 to x0 plus L of cosine 2 pi Rx over L times cosine 2 pi Px over L dx is equal to L for R is equal to P, which is equal to 0. It is equal to 1/2 L for R that is equal to P but is greater than 0. And it is equal to 0 for R that is not equal to P. The third property is that the integral from x0 to x0 plus L of sine 2 pi Rx over L times sine 2 pi Px over L dx is equal to 0 for R that's equal to P, which is equal to 0. It's equal to 1/2 L for R is equal to P, but greater than 0, and it is equal to 0 for R that is not equal to P. Where here, your R and P are integers greater than or equal to 0. Later, we will be using these properties here to simplify some expressions. Eventually written as the following. We have f of x is equal to a naught over 2 plus the sum from r is equal to 1 up to infinity of ar cosine 2 pi rx over L plus br sine 2 pi rx over L. So this function here is what we're going to use later to express complicated functions in terms of the sum of sines and cosines. Where here, your a naught, ar, and br are called your Fourier coefficients. These coefficients are analogous to those in a Fourier series expansion, and the determination of their numerical values is the essential step in writing a function as a Fourier series. Our next job is to find what a naught, what ar, and what br is. Now let us find out what your Fourier coefficients are. For a periodic function f of x of period L, we will find that the Fourier coefficients are given by the following. Your AR is equal to 2L times the integral from x0 to x0 plus L of f of x cosine 2 pi Rx over L times dx. And your BR is equal to 2 over L times the integral of x0 or times the integral from x0 to x0 plus L of f of x sine 2 pi Rx over L dx. If you're going to use other references, you'll find that there are other expressions of your AR and BR. But for this class, we are going to use these expressions here. Remember that we are using the book by Riley, Mathematical Methods for Physicists and Engineers. Here, your x0 is arbitrary, but is often taken as 0 or negative L over 2. and the apparently arbitrary function factor 1/2, which appears in the a naught term in equation 12.4, is included so that 12.5 may apply for r equals 0 as well as r is greater than 0. So please remember this Fourier coefficients here. Let us derive the relations 12.5 and 12.6, or let us derive your Fourier coefficients AR and BR. Suppose that the Fourier series expansion of f of x can be written as in this one here. So let's start from your beginning function. Then we multiply this function by cosine 2 pi px over L, and then after that we integrate over one period in x, and changing the order of the summation and integration, we get the following expressions. So on the left hand side, we multiply 2 pi px over L, and then we integrate from x naught to x naught plus L. On the right hand side, we also multiplied cosine 2 pi px over L. So you have a naught over 2 times the integral of this function here, and then we also multiplied your cosine 2 pi px over L to your AR term, and we also did multiply your cosine 2 pi px over L to your BR term. And then we have this expression here. We can now find the Fourier coefficients by considering equation 12.7 as p takes different values. Please have a look again at the following orthogonality conditions, as we are going to apply this one to the previous function. So we have this function here multiplied by your cosine 2 pi px over L on both sides of the equation. Using the orthogonality condition from 12.1 to 12.3 of the previous section, we find that when p is equal to 0, this equation just becomes your f of x dx is equal to a naught over 2 L. So from here, we can now find your a naught term. So your a naught term is just equal to your 2 over L times the integral of x naught, or times the integral from x naught to x naught plus L of f of x dx. Again, from the same function, when p is not equal to 0, the only non-vanishing term on the right-hand side of this equation occurs when r is equal to p. Applying your orthogonality conditions, we get that you have the integral of x naught, or the integral from x naught to x naught plus L of f of x cosine 2 pi rx over L dx, that's equal to AR over 2 times L. So what happens is, when r is equal to p, this one here becomes r, and this equation stays the same or is left unchanged. And this one here, this first term on the right hand side becomes 0, because if we integrate a cosine or a sine function over one period only, it will become 0. So this one is 0, and this one is also 0 from the orthogonality condition, while this one here, this is equal to your L over 2 times your AR. Thus, you have this expression here. You have the integral from x naught to x naught plus L of f of x cosine 2 pi rx over L dx is equal to AR over 2 times L. Taking out your AR is equal to 2 over L times the integral from x naught to x naught plus L of f of x cosine 2 pi rx over L dx. So this one here is your AR coefficient. The Fourier coefficients BR may be found by repeating the process previously, but multiplying this time by your sine 2 pi x over L instead of cosine 2 pi x over L. So we start with the same expression. We just multiply this one by your sine 2 pi px over L. And then integrating over one full period in x and changing the order of summation and integration, we get this one here. So this one is multiplied by sine 2 pi px over L, and then you integrate over one full period. So you have the integral from x naught to x naught plus L of f of x sine 2 pi px over L dx. On the right hand side, so we multiplied here your sine 2 pi px over L, also this one here, and this BR term here. So we get these expressions here. You have a naught over 2, and the integral from x naught to x naught plus L of sine 2 pi px over L dx plus your AR term multiplied by sine 2 pi px over L, and then integrating over one full period from x naught to x naught plus L, and then your BR term multiplied by your sine 2 pi x over L. So this is again the function that we got after multiplying your sine 2 pi px over L to your original function. If p is equal to 0, all the equations will be 0. This will become 0, this will become 0, this will become also 0, and this is also 0. The same as if your r is equal to p that's equal to 0. And the only solution will be only when your r is equal to p, which is greater than 0. And from this solution here, the only non-vanishing term of the equation will be the third term. That is, here the first term is 0, because again, if we integrate a cosine or a sine function over one period only, it will be 0. The second term is also 0 because of the orthogonality condition. And the third term is equal to bn times L over 2. Playing with your equation to get your bn is equal to 2 over L times the integral of x naught, or the integral from x naught to x naught plus L of f of x sine 2 pi px over L dx. Let's have an example. Express the square wave function illustrated as a Fourier series. So we have this square wave function here, and what we are asked is to express this one in terms of your Fourier series. The square wave may be represented as the following. You have your f of t is equal to -1 for t that's greater than or equal to -1/2 t and less than 0. So it's -1 for these values of t here, and it's equal to +1 for 0 is less than or equal to t, and t is less than 1/2 t. So these are your f of t is equal to +1, and this one is equal to your -1. Physically, this might represent the input to an electric circuit that switches between a high and low state with a time period t. So you have here, you usually see this one in alternating current circuits. And in deriving the Fourier coefficients, we note that firstly, that the function is an odd function. So this one is actually an odd function, and so the series will contain only your sine terms. Again, for your even function, your series will contain your cosine terms, and for your odd functions, your series will contain your sine terms. So for this square wave here, if you're going to write this one as a Fourier series, your Fourier series is expected to contain only your sine terms. Since your square wave is an odd function, only sine terms will be expected to be present in your Fourier series. And the only term containing your sine terms in your Fourier series is the term with your BR coefficient. And again, remember that your BR is equal to 2 over L times the integral from x naught to x naught plus L of f of x sine 2 pi r x over L dx. And let's solve for B1. But first, let us rewrite your BR in terms of the given conditions for your square wave. So again, we have this one here. These are the given equations. So you have your f of x is equal to -1 for this condition here, and it's equal to +1 for this condition here. So rewriting this one, where your L now this time is equal to t, your period. So your BR is equal to 2 over t times the integral from -t over 2 to t over 2, because as you can see here, the function is defined from -1 over 2 to -1 over 2t to 1/2 t. So this will now be our new limits of integration. So this integral here of f of t sine 2 pi r t over t dt. So this will now be our BR term. We're going to use this one to solve for your B1. So B1 is when your r is equal to 1. So you have 2 over t times the integral of f of t sine 2 pi t over t dt. And we divide this expression here using these conditions here. So we divide your integration limits from -2 over 2 to 0, and then the other half will be from 0 to t over 2. And remember that from -t over 2 to 0, your f of t is equal to -1. That is why here you have your -1. And from 0 to 1/2 t, your ft is equal to 1. So that is what we have here. So your b1 is equal to 2 over t times the integral from -t over 2 to 0 of -1 sine 2 pi t over t dt plus integral from 0 to t over 2 of 1 sine 2 pi t over t dt. Simplifying further, your b1 is equal to 2 over t times negative the integral of sine 2 pi t over t evaluated from -t over 2 to 0 plus the integral of sine 2 pi t over t dt evaluated from 0 to t over 2. So this one again is your b1, which we have earlier. And to solve for the integrals, let us let u be equal to 2 pi t over t. Then your du is equal to 2 pi dt over t. And from that, your dt is equal to t over 2 pi du. So your integral of sine 2 pi t over t dt will then become your t over 2 pi integral of sine u du, where the integral of sine u du is equal to negative cosine u. So this integral here is equal to t over 2 pi times negative cosine u. We go back again here, where your u is equal to 2 pi t over t. Then the integral of sine 2 pi t over t dt is equal to t over 2 pi times negative cosine of 2 pi t over t. So we are going to use this one here for this expression here. So from this one, we now evaluate your integral. So we can write or we replace this integrals here with the values. Okay, and then you evaluate from negative t over 2 to 0 on one end, and the next term we evaluate from 0 to t over 2. We can take out your t over 2 pi out of the equation or out of this brackets here. So we have 2 over t times t over 2 pi times cosine 2 pi t over t evaluated from negative t over 2 to 0 minus cosine 2 pi t over t evaluated from 0 to t over 2. So evaluating, we get for v1 is equal to 1 over pi of 1 minus negative 1. So it's 1 plus 1. So first is you have cosine 0, this 1, minus cosine of 2 pi t over t evaluated with negative t over 2, which is equal to negative 1. So you have 1 minus negative 1. So that's 1 plus 1 minus this term here. We have cosine 2 pi t over t using or replacing t over 2 to t here. We get negative 1 minus cosine 0, which is 1. So you have negative 1 minus 1. So negative 1, or you have or you have 1 plus 1 minus negative 1 minus 1. This is equal to 4. So your b1 is equal to 4 over pi. This one here is your first term, or your first b coefficient. Now let's solve for b2. We use the same br that we have earlier. But this time, let's let r be equal to 2. So if r is equal to 2, then you have 2 over t times the integral from negative t over 2 to t over 2 of f of t sine 4 pi t over t dt. So we divide these integration limits to from negative t over 2 to 0, and then from 0 to t over 2, just like we did earlier. And we evaluate these integrals with just the same process. So evaluating the integrals, you get 2 over t times t over 4 pi times cosine 4 pi t over t evaluated from negative t over 2 to 0 minus cosine 4 pi t over t evaluated from 0 to t over 2. Evaluating, you have 1 over 2 pi times cosine 0, that's 1, minus cosine 4 pi t using negative t over 2 as your small t over t. So that is 1. So you have 1 minus 1 minus this term here. You have cosine 4 pi t over t using t over 2 as your small t, which is equal to negative 1 minus cosine 0, that's 1. So we have negative 1 minus 1. This one here is equal to 0. Thus, your b2 is equal to 0. We can solve for r up to infinity, but in general, for br, you will find that you can have this expression here. So this is the general form for the solution of your br. you have 2 over pi r times 1 minus negative 1 raised to r, and the sign coefficients are 0 if r is even. As you can see, for b2, this is 0. So for b4, it's also 0. For b6, it's also 0. And this is equal to 4 over pi r if r is odd. Like say, for example, for your b1, you have 4 over pi. Hence, the Fourier series for the square wave function may be written as the following. So we have this one again, but we know that your a naught is 0, your ar is also 0, because your function is an odd function, so we only have this one here. So the first term is you have for your b1, so b1 is 4 pi times sine 2 pi x over L, plus your b2, which is 0, plus your b3 here, plus your b4, which is 0, plus your b5, this term here. Here, your 2 pi over t was just replaced by omega, which is called your angular frequency. So this one here, so this function here is your Fourier series for your square wave. So that is an example of how you're going to write a complicated function in terms of a Fourier series. It is often the case that the function we wish to express as a Fourier series has a particular symmetry, like in the square wave, which we can exploit to reduce the calculation labor of evaluating Fourier coefficients. Functions that are odd in x have no cosine terms, and all the a coefficients are equal to 0. Functions that are even in x have no sine terms, and all the coefficients are 0. Again, functions that are odd, like your square wave in x, have no cosine terms, and all the a coefficients are equal to 0. So your a naught and then your a naught and then your ar is equal to 0 for your odd functions. Functions that are even in x have no sine terms, and all the v coefficients are 0. That is your br is equal to 0. The Fourier series expansion usually works well for functions that are discontinuous in the required range. However, the series itself does not produce a discontinuous function, and we state without proof that the value of the expanded f of x at a discontinuity will be halfway between the upper and lower values. Expressing this more mathematically, at a point of finite discontinuity xt, the Fourier series converges to 1/2 the limit of f of xt plus epsilon plus f of xt minus epsilon as epsilon approaches to 0. At the discontinuity, the Fourier series representation of the function will overshoot its value. Although, as more terms are included, the overshoot moves in position arbitrarily close to the discontinuity. It never disappears even in the limit of an infinite number of terms. This behavior is known as your Gibbs phenomenon. These are examples of the convergence of a Fourier series expansion of a square wave function, including one term. So if you remember earlier, if you only express your square wave with your b1 coefficient, you have this curve here. So your b1 coefficient is not actually enough to define your square wave or to model your square wave. If we include your uh, if we include two terms, so your b1 and b3, this is what you get, which is still not close to your square wave. If we include three terms, this is now what we get. And for 20 terms, this is what we get. The overshoot of delta is shown in this model here. As you can see, even if we are going to include up to infinite number of terms, we will not really match the exact square wave, as we are still going to see some overshoots in your function. So this is again your square wave, and we model this one using your Fourier series for n equals 1, or for just one term. This is the summation wave for two terms of n equals 3. This is your sum wave for 9 terms. This is your sum waves. So this is actually what happens with your Fourier series as you include more terms. So it approaches to your square wave more closely, but still we cannot get the exact square wave, as we still have overshoots or uh, overshoots in your discontinuous function. So this one here are your overshoots. Fourier representation may sometimes be used for non-periodic functions. If we wish to find the Fourier series of a non-periodic function only within a fixed range, then we may continue the function outside the range so as to make it periodic. For example, in figure 12.4b, it shows the simplest extension to the function shown in figure A. So if this is your function from 0 to L, we can extend this one to make it periodic, as in your figure B here. However, this extension has no particular symmetry. So as you can see here, wherever you put your vertical line here, you will not see any symmetry. Figures 12.4c and d show extensions as odd and even functions, respectively, with the benefit that only sine or cosine terms appear in the resulting Fourier series. So we extended your non-periodic function here as an odd function. This is how it will look like as an odd function, and this is how it will look like as a sine function. We note that these two extensions give a function of period 2L, and we can now see symmetries for both your last two extensions. Let's have an example. Find the Fourier series of f of x that's equal to x squared for 0 that's less than 2x and x is less than or equal to 2. So this one here is your x squared function. As you can see, this is a non-periodic function. And the first thing that we need to do is to make this function periodic. We do this by extending the range of interest to -2. So if we extend it to -2 in such a way that your range now is from -2 to 2, in such a way also that your f of x is equal to f of -x, then letting your f of x plus 4k is equal to 4x, where k is an integer, and we have this function, an even function with period 4. So we make extensions to the left to make an even function with period 4. And we can now write this one as a Fourier series. Note that since we have made the specified function even by in x by extending the range, all the coefficients BR will be 0. Because if you remember, your sine function, which contains your BR, is only for your odd functions. Now we apply your 12.5 and 12.6, your AR, and then your BR coefficients with your period L is equal to 4 to determine the remaining coefficients. However, since it is an even function, so all your BR terms is equal to 0, and you are only going to solve for your AR. So your AR is equal to 2 over 4, where your L is equal to 4, times the integral from negative 2 to 2 of x squared cosine 2 pi r x over 4 dx. Your f of x here is equal to x squared. This is just equal to dividing this limits into 2. So we can just evaluate from 0 to 2 as this function here is an even function, but we just multiply this one to 2 to also take note from the interval of negative 2 to 0. So this one is just equal to 4 over 4, or 2 over 4 times 2 of the integral from 0 to 2 of x squared cosine pi r over x over 2 dx. Again, what we just did here is that we divided this integration into two halves, where we will evaluate only from 0 to 2. And this is true because your function is an even function, so it just mirrors. So we just multiply by 2 to also take note of the other half. Solving for AR by integrating this term here, your x squared cosine pi r x over 2, you can solve it by yourselves or by using your integration table. You get this value here of your integral. So that's 16 over pi squared r squared cosine pi r. And cosine pi r is equal to negative 1 r raised to the power of r. So we have 16 over pi squared over r squared. So this is your AR. And as you can see, if you want to evaluate for your a's of 0 or your a naught, since you have your r squared term here, if you have 16 over 0, it's undefined. So to find or to evaluate for your a naught, we must return to the original definition. So this is again your original definition. And let's find for a naught, or when your r is equal to 0. So when your r is equal to 0, cosine 0 is 1. So you're just left with x squared dx. And evaluating this integral, you get 8 over 3. Now we can write the final expression for your f of x, which is then from this one here, where your b is equal to 0, you just replace your a naught with 8 over 3. So that's 4 over 3 plus your AR. So this one here is your AR times your cosine 2 pi r x over L, or you have cosine pi r x over 2. With your L, that's equal to 4. And this is now your expression of your f of x as a series, or as a Fourier series. Let us end this discussion here, and for the next discussion, let us discuss your complex Fourier series.